Thank you very much for inviting me to this conference. I think it's a wonderful program. And since I've been working on, for a number of years now on an interaction between macro and climate change, I've been invited to many of these conferences where I get to meet economists and physical scientists from all different disciplines, which I find really useful. All right, so today I'm presenting a paper called Climate Change Around the World, joint with Per Krusell. And the goal of the paper is to construct a global, dynamic, general equilibrium model of interactions between the economy, climate, and weather at a degree of resolution geographically that's very high, so 1 degree by 1 degree regions. You can view the model as extending Nordhaus's DICE and RICE models, where RICE stands for Regional Integrated Climate Economy Model, which have very little or no regional detail, to a dynamic, modern general equilibrium setting with many regions. And then we want to use the model as a laboratory to quantify the distributional effects of climate change and climate policy. So the new elements here are many, many regions and looking at distribution across space. And the long-range goal, which I might get to a little bit at the end, is to eventually couple the Norwegian Earth System model, or NORI-SM2. I'm working with 2 climate scientists in Norway with this high-resolution economic model, so then we can actually talk about not just average temperature or climate, but can talk about variations around that path and include weather variables like wind and extreme temperatures and precipitation. That's ongoing work. If I have time at the end, I might have a couple slides on where we're going. But for today's paper, there's no weather, it's just simply economy and climate, viewed as average temperature. This is part of a growing literature on spatial models of climate change, allowing for adaptation across space, which I think is an important aspect of adaptation, not the only one, but one important one. And here's a partial list of references that I won't go over today, but you can see the list is, every time I present the paper, I'm adding another paper there. So this is just meant to illustrate that there's a lot of work working in this space right now. All right, so let me start with a picture of average temperature, annual average temperature in centigrade, the early part of the 20th century. And there are 19,000 1 degree by 1 degree regions here that make up this picture. And those 1 degree by 1 degree regions are the unit of analysis, or the agents in my economic model, and they're going to interact through financial system and through emissions. All right, so we're starting off there, and you can see there's huge heterogeneity in average temperatures. Now let me show you the log of GDP, or gross regional product, in each of these 1 degree by 1 degree cells. This is from Nordhaus's GECON database. So again, there's large differences, heterogeneity in space and GDP across regions. All right, so let me plunge. So that's just to give you a warm-up. I've tried to put the whole model here on one long slide with no equations. So the idea is that we are, like in the DICE model, we're going to emphasize capital accumulation and consumption savings decisions, along with an explicit model of energy use. So in each region, you can view there as being a representative consumer, but then we have 19,000 heterogeneous these consumer entrepreneurs interacted around the globe. So we have forward-looking consumers and firms in each region who make consumption, savings, and energy use decisions. There's no migration in this model, but there is movement of capital, or differing patterns of capital accumulation, physical capital accumulation around the world. We have new classical technologies for producing final goods and energy, and these use capital, labor, and energy as inputs. We're going to think of energy as coal, so non-exhaustible, produced according to this production function that we specified in the second point there. We're not worrying about hoteling rents on, say, limited supplies of oil. Now, the key part of the way the model works is that regional TFP, total factor productivity, is going to be the product of an exogenous component, which is capturing those huge differences across gross domestic product across regions, plus, or times, another component that we're going to assume varies with regional average temperature. All right, so there are going to be local impacts of climate change coming through regional average temperature, and I'll be much more explicit about exactly how that works shortly. In this model, as I said, there's no migration, but there is movements of capital. All right, so we're going to look at 2 polar cases. One is autarky, where actually there is no movement of capital, so each region is on its own, but still connected through global emissions, through the climate system. And another extreme case of unrestricted borrowing and lending. And I'll get back to that later, why we look at those 2 cases. So in a summary, this looks a bit like an Iagari-Angelettos model, which is where I come from, actually. Some of my earlier work was studying heterogeneous macro models with heterogeneity across households. Here we're bringing that machinery, or that set of tools, into the climate literature. There are no shocks here, so there is no weather, as I said, although we're working on that, and they can be easily added. So we do have adaptation here of a certain form. One is consumption smoothing, so regions can save and consume in response to how they view climate change affecting their productivity in the future. That's present in the DICE model as well. But what's new here, when we're not in autarky, is capital mobility, which also allows for leakage. So if different regions have different climate policies, which we can also handle in this framework, then capital can flow in response to that. All right, so that's the economics part. As far as the climate system and the carbon cycle, we have a very simple setup where global average temperature varies with the global stock of atmospheric carbon, and then the stock of carbon obeys the linear law of motion driven by global emissions of carbon. All right, so in the economic model, regions are emitting, they're all small, emitting carbon in the atmosphere. That carbon in the atmosphere, as we know well, affects the stock of carbon, which then affects global temperature. There's another way to model this is the global temperature varying linearly with cumulative emissions since the Industrial Revolution. We use the first two, but you can alternatively use the third, and we're going to use that in the later work with the climate scientists. And then locally, how do things work? So regional average temperature drives total factor productivity in that region, and we're going to let it vary linearly with the global temperature being what's called a pattern scaling or statistical downscaling relationship with region-specific slope coefficients, which we have asked climate scientists to compute for us. And these are all reasonable simplifications of the dynamics of Earth system models. Okay, so you tell climate scientists what we're doing here. They think it looks reasonable. It's not capturing the full complexity of an Earth system model, but it's a reasonable approximation. All right, so let me show you these coefficients I mentioned, which govern how regional temperature varies with global temperature. So imagine that the global temperature increases by 1 degree in centigrade. By how much, say, would northern Russia or, say, Chile, according to this map, by how much would its temperature change locally? And you can see there's huge heterogeneity. This is well known by now, and it just comes right out of data and climate models. But so the northern regions of Russia are going to warm by much more than is Chile or other parts of the world. So there's big heterogeneity. So we have three dimensions of heterogeneity. We have different initial temperatures, all right? And then we have different levels of GDP in all the different regions. And then we have this heterogeneity and sensitivity to how your local temperature varies with the global temperature. All right. So later I'm going to have a model which, and first I'm going to get some water. Excuse me. Sorry about that. So later we're going to have a model in which we run out the global economy at this high degree of resolution, and then you'll see precisely this map reappearing. I won't show it today, but just remember it. When the globe warms by 1 degree, that shows exactly how much the different parts of the globe are going to warm. Okay, so we have a global equilibrium here. So I just want to make an aside too. This is like the diametric opposite of Jim's fantastic overview earlier. I'm presenting a very specific paper here, but I think has some provocative findings about spatial aspects of climate change, which I think have been corroborated or seen in other types of work too, that people in this room even. So, okay. So just to talk about equilibrium conditions, so the idea is that we have these forward-looking consumers. So each region sort of makes optimal decisions on consumption savings and energy use, taking as given a path of the global temperature, which then determines their regional temperature, which is what they care about, and the interest rate when we have financial markets. And then, given these decision rules, you can run the model forwards, and I'll show you one short simulation later. So then the implied path of global emissions must generate the path for global temperature. That's a perfect foresight assumption here. And the global bond market clears in every period. That's the interest rate adjusting to do that. So with free capital mobility, one thing we quite like about this model, in a way, it's just a short step away from the DICE model or the Golosov, Hassler, Kusel, and Savinsky model in econometrica that is sort of a modern macro counterpart of the DICE model. With free capital mobility, the model aggregates. So we only need to solve the problem of a global stand-in consumer taking the global temperature as given. That makes that model quite easy to solve. And there's a sense in which it exactly nests the DICE model then. It really is, if we calibrate it as the DICE model is calibrated, then it really is the DICE model. Or in a more modern parlance, it's the Golosov model because it aggregates. But in autarky, it doesn't aggregate. And so then we need to solve 19,000 dynamic programs, one for each region. They each have a different path of their productivity going into the future. So that leads them to solve different problems. Remember, they have a different initial temperature and a different sensitivity to that global temperature change. So they all have differing paths of productivity. But this is not too hard to do on a parallel computer. All right. So now, what about our damage specification? So there's a lot of work here, and this may probably, as everyone in this room knows, is the weakest part, I would say, of the economy climate literature. What we're going to do is take a somewhat different approach. Is we're going to imagine that the damages in region I, okay, let me back up. That's not the different approach. We are assuming that the damages in region I depend only on their local temperature. I've already alluded to that. So total factor productivity in region I is a function, D, of local temperature. And that function is going to be common across all regions. And it's going to have an inverse U shape, which varies between 0 and 1. So you can imagine its variation relative to the exogenous component of regional TFP. And when the temperature changes, you have a varying productivity relative to that. And here's the new part. We're going to reverse engineer this. So rather than do a top-down estimation or a bottom-up estimation, I applaud all those efforts, we're going to instead do something different. We're going to reverse engineer this U shape so that the high-resolution model generates aggregate damages from changes in the global temperature that match, say, what comes out of Nordhaus's DICE damage function or some other aggregate damage function. We're using Nordhaus's today. That's probably a bit low relative to the literature now. We could use a different one. But the point is that the idea of doing this, the methodology doesn't depend on matching Nordhaus's DICE function. It's more the idea of doing reverse engineering. So I guess the view there is we might trust somehow these aggregate damage curves as being reasonable, and then we want to come up with a local damage function that's kind of consistent with that. All right, and if someone were to present us with a different aggregate damage function, we'd be happy to use that and plug that in here. In some sense, all these models have to have that kind of consistency, and we're just reverse engineering. All right, so let me just show you. So remember, so it's all a drag on TFP. And I'll take the points from earlier that GDP is not welfare. Here we look at consumption, but even consumption isn't welfare. So, but nonetheless, that's our assumption throughout. Here is then our calibrated regional U-shaped damage function, the function D. And the idea is that there's an optimal point at which to operate. So we look only at level effects here, not growth effects as in some of Marshall's work I know, so sitting right in front of me. But we look only at level effects here. Although Marshall kind of gets curves that don't look so different from this in some sense. So, but there's a different methodology. So we calibrate this, right, to match these aggregate damage curves so we get the right convex shape. And so it comes out in the calibration that, so the model generates this so that there's an optimal temperature to operate at 12 degrees centigrade annual average temperature. And then you see that if you fall away from that optimal temperature, your productivity relative to your exogenous component of your TFP, in which there's huge variation, as I mentioned earlier, changes. It falls off from there. All right. So the way to think about this, imagine that there's, a region in Russia at 0 degrees today. So its productivity is 0.5 relative to its exogenous component. And then maybe the globe warms by 2 degrees, and that part in Russia warms by 8 degrees or 6 degrees, which is quite conceivable. Then it would move from 0 to 6 in this picture, and its productivity would change from 0.5 to maybe 0.75. And that would lead it to accumulate capital differently. When they're international capital markets, it also attract capital from elsewhere. places that are declining in productivity. All right, so this is an important curve. Let me try and suggest to you that it seems reasonable. So here's a picture which we then looked at to see whether it seemed reasonable when this passes the smell test. So you can see here that the highest productivity region, so 100 means you're near the peak, are exactly kind of where you'd expect them to be. It goes through New York, a good chunk of Europe, through Tokyo, Beijing, Australia, the southern part of South America. So, and then the low productivity areas are, say, northern Russia, where it's super cold, or the Sahara, where it's super hot. All right, so this picture kind of seems to be reasonable, and note we didn't calibrate to that picture. That was like, okay, we're done with the calibration. What does the picture look like? And we think it seems reasonable. All right. Let me. It's important here for the welfare effects to note that, and again, it's another check on this, is that most of GDP, 22% of world GDP in 1990 is taking place like near the optimum. So it'd be a little odd if that weren't the case. It'd be a strange calibration. And then not much GDP is happening, not much output is happening at places with lower regional TFPs, either because they're very hot or very cold. All right, but importantly, a large share of the global population is living in places with regional GDP that's quite low. And so this will actually drive some of the welfare results, as you see shortly, and it kind of gets at some of these inequalities, ideas of global inequality and how it relates to climate change. All right, so because many of those people living at low regional TFP are living in hot places. And you can see that if you live in a hot place, going back to this picture, if you live in a hot place, then you don't want to get hotter. It drives you down. If you live in a cold place, you might not mind getting a little warmer. All right? So there's heterogeneity here, and that's what we're trying to study. So let me just make a few comments on the model. All right, just to kind of review a little bit. So at the aggregate level, this spatial model with free capital mobility nests the DICE model. Agents make forward-looking decisions anticipating future climate change, so just as in the DICE model. Regional damages are assumed to have an inverse U-shape, calibrated to match aggregate damages, in this case coming from the DICE model. Spatial adaptation takes place through differing patterns of capital accumulation across regions. And here I want to get back to something that Jim said when discussing, say, models of adaptation, that we think it's quite important to write down, this is what the macroeconomists can bring, I think, is to write down a fully specified microfounded model that permits quantitative analysis of behavioral equilibrium responses to counterfactual changes in climate policy. So we have a handbook paper in the Handbook of Macro and Environment and Macro. We kind of make this point that measuring the marginal externality damage of carbon emissions, say, keeping behavior constant in a given allocation, is not the same thing as the optimal social cost of carbon. Right? So those are two different ideas. And so you need a model that's going to allow for these behavioral responses. All right, and then we built one that allows for some aspects of adaptation, but not others. All right, so let me talk about the experiments we're going to do. And I'm actually going to come back to this first point about free capital mobility here and autarky. We got a surprising result there. All right, so experiments, we're going to do some laissez-faire experiments, so no carbon policy. And then we're just going to have a policy experiment where every region imposes a common path for carbon taxes, and we view it as financed locally. So there are no interregional transfers, that the revenues are just rebated locally. And throughout, we're mainly going to focus on relative effects, not aggregates, because by design, the model is kind of supposed to look like other representative agent or one consumer models. So at the aggregate level, not much is happening. Where things are happening is in the relatives. So here are the main findings. I could just stop there, I suppose, but I'll flesh this out a little bit. But this is important. So this is what we find, that climate change affects regions very differently. The stakes are big at a regional level. Now, when we first started doing this too many years ago, I think that was a little bit provocative. I think now more and more estimates from different approaches are finding, in fact, that regional heterogeneity is large. And this is like another take from a different methodology that kind of confirms some of those findings. So, for example, although an optimal tax on carbon, here what I mean by optimal is what would be optimal in the DICE model. So if you have free capital mobility, you can aggregate this model up to a representative global consumer and imagine, and don't worry about distributional issues, find a global tax that maximizes that welfare of the standing consumer. So it's probably a little bit lower of a carbon tax than what is standard in the literature now. In any case, what we find is large disparity of views. Many regions gain, many lose. All right? The average consumer gains, but there's heterogeneity across regions. We also find that the findings are very close for two extreme market structures. So actually it turns out it didn't make a whole lot of difference. And the reason here is that regions can respond optimally to how they perceive their productivity changing in the future. And they have a high elasticity of substitution between today and tomorrow. So they're quite willing to shift capital around. And it turns out that they end up in an allocation that pretty much equates marginal products of capital across regions. So there are some differences, but they weren't very pronounced. So given our calibration, and also given that climate change is happening relatively slowly here, you have time to adapt through consumption smoothing. So it turns out those two market structures didn't give a very good different answer, which was nice for us because then we didn't have to think about so much like how do you do an intermediate case and what are the frictions that might impede financial markets. So we're going to look pretty much just the rest of the talk on free capital mobility. Climate change leads to large increases in global inequality in GDP per capita is another finding, so we can use the model. And the tax on carbon mitigates these increases only to a small degree. So I'll show some of these pictures. First, let me show just one global picture. This is showing global emissions of atmospheric carbon in gigatons. The top line is with no taxes. And remember back from my slide, and maybe I didn't even say it about how the model works, we imagine we don't want to, we're pushing in the spatial heterogeneity dimension, we're not pushing in any other dimension. We just imagine that there's a green transition happening exogenously. So eventually things become green, we're not modeling that, but we think it's important to calibrate to something like that. So eventually all emissions through whatever technologies become green, or there are no emissions. That's why there's a hump shape there at a certain point. And then with a carbon tax, you see that you reduce emissions dramatically, and eventually they all go to zero through a green or backstop technology that eventually comes online. All right, so these pictures look exactly like what would come out of a similarly calibrated DICE model. All right, so now we'll get to some pictures. So I'll just show one set of pictures here. If you want to see a whole set of movies, you can go to my website. Normally I would click on that link, but I'm afraid it wouldn't work, so let's just, we'll just click through it. So I'll click through an example that kind of results, and I actually find these pictures very instructive because it's a lot going on. It's hard to get your mind around a big matrix of numbers, as we were just discussing earlier. So here is showing 10 years out, according to the model, GDP relative to a long-run growth path of 1% assumed here, so no growth rate effects, just level effects. So relative to that path, is your GDP lower or higher than it would have been? And here you can see that at 10 years out, some regions have gained in productivity and so are gaining in GDP, and some are losing slowly, not quite yet, but we'll click through this, and then you can see that, not surprisingly, Russia, now you can already see Russia's gaining a lot. It's getting warmer there. That makes it more productive according to our model. So more capital is going to flow there and be accumulated there, and GDP is going to grow there relative to the trend path. Whereas a hot place like the Amazon or the outback in Australia or parts of Indonesia or Sahara are losing because their productivity is declining because they're already hot. All right, so you see this big heterogeneity, and then you can click this out a number of periods, and now we're getting to the point where emissions have peaked, and emissions are going to slowly decline, and so the temperature is going to come back down a little bit. Some of the emissions are assumed to last forever, so the temperature asymptotes at a new higher level. I didn't want to go to that picture yet. All right, so that's the final resting point 300 years out boldly. So the idea there's this huge heterogeneity, and it kind of mirrors the picture that we saw for temperature and for sensitivity. All right. So now, okay, so that's an example. You can see more examples of other variables. So we can play out this economy and see how it goes. Now, welfare gains from taxation. So this picture looks kind of the same too. So now, because we have a fully microfounded model, we can ask, okay, we impose this carbon tax uniformly across all regions. It's rebated locally. Who gains and who loses? You can see that Russia actually loses from a carbon tax here. It loses because the carbon tax slows down warming, and they actually like warming there. They'd like to warm a bit. There was even a Putin quote at one point along these lines that I no longer include in my talk, but that was suggesting that from a conference many years ago. Meanwhile, say, Sahara is very much in favor of the carbon tax because it slows down warming, and they're already hot and are losing productivity. There's huge heterogeneity then, and I wanted to go back actually to this final picture too. You can see here that here the GDP changes, some of them are quite large. It's not 10%. Regionally, there's way more at stake here. It's not 10%. It could be 30% or 50%, either direction. So there's big changes regionally that kind of dwarf the global changes. All right, you can also do this. You can also add up welfare changes in different ways. So how do you aggregate up to a globe? So if each region gets one vote, as I said, 56% gain. If each person gets one vote, it's 84%. It's because many people are living in hot places. You could do this different ways. You could say $1 gets one vote. You could take the average gain weighted by regional GDP or by regional population. I don't know quite the right way to aggregate this, but the point is that there's a distributional effects. And so policymakers would need to think about those distributional effects as well. And I'm not... some people I know have worked on how to do that. I'm not doing that in this paper, how to aggregate up and maybe account for inequality. One final picture is you could aggregate to countries. So this is percentage of consumption again. I just want to go, if I go back to this picture here, just reiterating, these numbers on the right-hand side, I should have said that, are percentages of consumption per period. So you can see that when you're gaining or losing, it's by pretty big numbers, but a macroeconomist would view as pretty big numbers. So permanent changes in consumption of 4% per year are not uncommon across the globe. All right, that's in consumption per year. All right, so you could aggregate this up to countries, and again, you see huge heterogeneity. It's not so dissimilar from the previous picture as well. All right, so let me, moving right along here. I will still have a few minutes left, so let me show another set of results, then some caveats, and then maybe mention a little bit about what I'm doing in the next stage of the work. So here we can look at inequality. So we're looking at per capita GDP by country using the 90-10 percentile as a measure of inequality. So that starts out at about 32 in 1990. And the top line with the triangles is with laissez-faire, so no types of policy at all. There is green technology coming online, but there's no policy designed to accelerate that. So, inequality increases to 46 by this ratio. So large an increase in inequality. And you can't really get that number without having a full-fledged model, a macro model of how the macroeconomy is going to evolve under climate change. And surprisingly here, although the optimal tax has a big effect on emissions, it doesn't really have, and on regional heterogeneity, it doesn't affect inequality though, so somehow. So there's regional heterogeneity, people feel differently about the carbon tax for sure, but inequality doesn't really change that much, all right? So these are the kinds of counterfactual experiments that one would like to use a model for. So takeaways. So climate change in this model is about relative effects much more than average effects. Admittedly, those may be somewhat small here because we're using the dice damage function and ignoring maybe other factors that might matter, as Jim was saying earlier. There are large disagreements on climate policy, and there's a methodological insight that is a quantitative point, but a useful one here, because it's not a general point. You can think of models where it won't work, and I explained some of the mechanisms earlier, but we thought the market structure, because it admits more or less adaptation, would be important for the results, but it isn't. All right, so building on the platform, we really view this as a long-range project, and there are, papers. There are many papers more and more papers studying different aspects of spatial adaptation, some with trade, some with migration, not so many with focusing on capital accumulation, but even there's some work. So in any case, we view this as a platform we can build on, and we think it's nice that it makes a sort of tight connection to the classic macro models of climate change. We're kind of like not moving too far away at once from that classic models, Nordhaus's Nobel Prize winning model. All right, so there's a sense in which the damages are too local here. So I know that this conference is partly about effects of climate change on ecosystems. I don't have that in this paper at all. It's all very local, unless the ecosystem is a very local ecosystem, but we think of ecosystems as involving whole regions of countries, not just small 1 degree by 1 degree cells. So we don't have that in the model now. We don't have enough heterogeneity and regional damages. You could imagine maybe some regions are poor is a possibility, or maybe there's rural versus urban, or at different types of production. Maybe they're affected differently with different U-shapes. We don't allow for migration, which is a hard problem, but we also think it's important that when you study migration that you retain forward-looking consumption savings decisions. I mean, that margin of adaptation is quite important here, so how do you merge those? But what I'll spend the last 3 minutes on here is just weather as well as climate. So climate is a probability distribution over weather outcomes. And weather can be, even global temperature is a very stochastic process. In other words, it's a lot of randomness, even the global temperature, even more so at the regional level. And then weather is really maybe more what we care about. We don't care maybe necessarily about average temperature. We may care about extreme weather events, extreme temperatures or floods or high winds. And so we want to bring in weather here into this type of model. Bilal and Rossi Hensberg, I think, are doing that. Jim mentioned this paper earlier. One of the few papers I know that's bringing that in, looking at detailed model of the U.S. economy by county. So, so one advantage of doing this is you can bring in these rich set of stochastic weather variables. Also, there's then no need to simplify the geophysics. There's some literature on economists capturing the geophysics of these Earth system models properly or not. We're just going to use an actual Earth system model. And then, what's useful here, why have a model with these climate risks here viewed as weather? So weather shocks are a climate risk. Does a hurricane hit this region and not that region? Do extreme temperatures, do they happen in one location or not another? Maybe they happen for several years, but then not for several years. So there's a lot of risk there coming through weather. And then we can use the model then to sort of study institutions for sharing these climate-related risks, because the model's all set up to do that. Maybe national governments can share climate risk somehow coming through stochastic weather variation. So I'll say, so here's just a picture. All right, so I did get to this. So this is a picture showing an error 1 coefficient for regional temperature coming out of these climate models. So it's showing so we're going to model local temperature not as a smoothly, continuously, so the average temperature in each region is going up smoothly, but around that there's some variation, these shocks to weather, and then it turns out that there's differing persistence. So the blue is very low persistence. So their annual average temperature has very little persistence from year to year. There's still this trend, remember, but now we're talking about variations around the trend. In other places, say parts of China, it seems, is very high persistence. So heterogeneity in weather and the persistence of weather shocks, and this is showing standard deviation of the shocks. So you can see, and these is in centigrade here, so these standard deviations measured in centigrade. So for some regions have very high volatility of shocks, some have very low volatility. So we want to bring in, as a first pass, just bring in that set of stochastic processes for local weather into the model. And in my last I love having the time right here, my last 42 seconds, my last slide. So computing equilibrium with weather is a challenging project. So that's where I'm headed now, so I'm glad I got a chance to kind of say where the project is going. This is really where our focus of our research now with the 2 climate scientists in Norway. So you can't embed an Earth system model into this macro model. It's just too high dimensional. So our idea, and I'd be happy to get feedback on this, is agents will form expectations of future weather using an approximation of the dynamics in NORI-SM2. Then we'll iterate backwards in the usual way to get decision rules based on the approximate expectations. But then when we simulate forwards, we'll use those decision rules and the actual dynamics of NORI-SM. And then we'll find a fixed point, as usual, in these macro models. But now it's not in the correct expectations, but in these approximate expectations. But it seems quite reasonable because I don't doubt agents are using the full dimensionality of an Earth system model to make their projections. So there are a couple methodological challenges. One is that these Earth system models have no shocks in them, which comes as a surprise to economists. Instead, they have nonlinear chaotic dynamics. It's all coming through changes in initial conditions and nonlinearity. It's quite surprising when you see it in practice. I knew this, but seeing it in practice is something else. So how can we use stochastic shocks to capture nonlinear dynamics? Also, there's a timing issue. When we run the model forwards, we have to link them, but the economic model runs on an annual time step, maybe at best monthly, whereas NURISM actually runs at a half-hourly time step. So that's where we're headed next. We've got some prototypes going, and please stay tuned. Thank you very much.